Hello students, good evening all. So welcome to our next session. So today, as I mentioned, today we are going to start a new chapter, that is binomial theorem. So this will be our first session in this particular chapter of binomial theorem. So far, just now we have finished our permutations and combinations. So where we have seen some like in C terms representation and all. So even in our while dealing with the combinations, we have seen NCR. So those representations and the corresponding expansion of it. So those things we have seen while discussing our concept of combinations. So again, while discussing our binomial theorem, we are going to discuss about that NCR, and also that will be again coming into picture here. Right. So yeah, some of you has joined. So meanwhile, remaining students join the session. We'll just have a quick overview of the topics that we are going to cover in our today's session of binomial theorem. So as it's our first session, so we are going to cover a very basic topics in our today's session, like the introduction part and all, and the very basic topics in our binomial theorem, like the introduction part here. So in that basic and introduction part, what and all topics that we are going to cover here. So let's have a look over that. So first we are going to start with this identities. So by looking at it, what is this identities and also there is nothing new in this identities. You guys are already familiar with these identities. So these identities are nothing but our simple a plus b whole square, a plus b whole cube and all. So I hope you guys are very familiar with all these identities. Yes or no? Right, so we'll just, because these identities will give our they will be the background for our binomial theorem. So in order to understand it quickly, we should have a look from our identities. Right. So once we have our identities, so using that identities, we can actually observe and we can conclude some statements. So for that, we are starting with identities and then we'll observe the identities and the relation between the expansions and the identities, and then we are going to conclude our things which are related to the identities. And the next here, using that observations or the conclusions based upon the identities, so we are going to form this Pascal's triangle and we are going to use this Pascal's triangle in order to write our binomial theorem. Right. So the next part here after the identities will be the Pascal's triangle and the next will be our binomial theorem. So we can say these two will be a background or the basic part in order to write our binomial theorem here. Right guys? So once we have started discussing our binomial theorem, so the next steps will be obviously related to that. So the next topic, the next concept which we are going to cover after the binomial theorem here is the deductions. So there will be slight changes here. So we have to just use this general binomial theorem which we have learned, which we'll be learning here, and then using that we'll be dealing some deductions from that binomial theorem. And then the next one here will be, obviously there will be properties. Right. So the next will be after the deductions from binomial theorem, we are going to discuss the properties of binomial coefficients. So here we'll be seeing while dealing with the binomial theorem, what are these coefficients and all. So there is no need to worry. So once we have that everything here, and the next we are going to discuss is the properties which are related to the binomial coefficients. And the next one here is, this will be the very important one, which is the general term in binomial expansion. So based on this general term, there will be numerous type of questions which can be asked in our JEE. So this general term is very important. So we have to observe this and then we have to understand this very carefully, and there will be no errors, no wrongs that we can do once we are familiar with this general term in our binomial expansion. So once we have a good grip in this general term in binomial expansion, whatever the questions related to this particular topic, we can easily crack them. Right. So these are the topics guys that I am planning to cover in our today's session. So let's see how it goes. So we'll just, I hope students has already joined the session. So let's just start with our today's session with the first topic, that is identities. So as I mentioned here, so there is nothing new here. This is all our identities, a plus b whole square, a plus b whole cube and all, as I mentioned. So here there will be a small trick. So in general, you will be learning a plus b whole square and all. So here I am just starting this power with 0. Right. So you have learned a plus b whole square and a plus b whole cube and all. So what I am trying to do is I am taking this power starting from 0. Right. So the first one here is a plus b whole power 0. That means anything power 0 will directly equal to 1. Right. That means here this a plus b power 0 will be equal to 1. And the next power will be 1, that is a plus b whole power 1. So that expansion will be nothing but equal to a plus b. And the next identity we are having here is a plus b whole square. So you guys are very familiar with this. So what is the expansion of this a plus b whole square, guys? So it is a square plus 2ab plus b square. And the next one, a plus b whole cube. Right, so the expansion here for a plus b whole cube is a cube plus 3a square b plus 3ab square plus b cube. Similarly, we'll be having the expansion for a plus b whole power 4, which is given by a power 4 plus 4a cube b plus 6a square b square plus 4ab cube plus b power 4. So by looking at this, all the identities here, so by observing all these identities and their corresponding expansions, can you guys conclude something? Can you relate something? And can you guys give me any observation that you identified from these identities which are given here? Anything. Whatever you feel like the difference or the, we can say a continuation flow, it's following a continuation thing, it's following a series, a sequence, like. So anything related to this which you are observed, you can just let me know. So let's see what you guys have observed from these identities. What are your observations? So I'll just give you a hint. Just observe the expansions and the powers related to our variables. That is what happens to the power of A and what happens to the power of B. So there might be 3 observations here. The one is related to power of A and the other is power of B, and the other one will be the coefficients of this AB. So these are nothing but the coefficients. So can you guys have a look and can you just state some of the observations, what and all observations you feel like from these identities? So take 2 to 3 minutes and just have a quick observation, keen observation, and let me know. So let's see the observations first. So the total number of terms in the expansion is 1 more than the index. So this will be our first and foremost observation from the identities which you have seen in our previous slide. So what is that? The total number of terms in the expansion is 1 more than the index. So let's see. So here, what is the index? So index is nothing but the power. So here for the first identity, power is 0. So here, what are the terms? How many number of terms in the expansion? 1. That means 0 plus 1 equal to 1. So let's get back to the second. So here, what is the index? 1. So 1 plus 1 is equal to 2. So in the expansion, we should be having two expansions, two expressions. So A and B. Similarly here, Index is 2. So 2 plus 1 is equal to 3. So we should be having 3 terms here. So a square, 2ab and b square. So 3 different terms. Likewise for here it should be 4 terms. So 1, 2, 3 and 4. Here there should be 5 terms. So 1, 2, 3, 4 and 5. So the first observation we can identify from this identities are nothing but the total number of terms in the expansion is always 1 more than the index. Right, so we have already seen the examples in our identities. Right, so let's see what is the second observation. So second observation here is powers of the first quantity, that is a, because we'll be writing the identities as a plus b. So this a will be the first quantity and this b becomes the second quantity here. So what is the observation here? Powers of the first quantity a go on decreasing by 1, whereas the powers of the second quantity b increase by 1 in the successive terms, which means the first term power is decreasing and the second term power is increasing. So let's get back to our identities and have a look again. So here, what is our second observation? Second observation is related to our terms, the powers of our terms. So what is the first term here? A, and second term here B. So if we take 0, so there is 0, so there is no need to worry here. So let's check here. So the power of A will be decreasing and this power will be increasing. So let's take the example here. A plus B whole square. Right, so what is the n index? That is equal to 2. So the first term A power will be starting from 2 and then it will be decreasing. So 2, 1 and 0. Whereas for the second term, it will be starting from b power 0 and it will be increasing. That is b power 0, b power 1 and then b square. So let's have a look here. So first the power of a here will be a square and then a power 1. Here a power 0 which is 1. Same with b here. So b power 0 which is 1. So there is no need to write, and b power 1 and b square here. Right, so the second observation here is whatever the element or the term which is present in the first place, the power of this will be starting from the index number and it will be decreasing until 0. And for the second one, it will be the reverse. So it will be starting from 0 and increasing until the index number. So let's check our a plus b whole cube. How the terms will be? So it should be a and b. So here what is the index? 3. So here it should be a cube and then b power 0. And next will be a square, b power 1. And next will be a power 1 and b power square. So b power 2. And the next will be a power 0 and b cube. Which means the terms should have the powers as a cube here. B power 0 will be 1. So no need to write a square b here. And then a b square here. And then b cube. So for as of now, just neglect the coefficients here. So let's focus on the variables here, the terms here, right? So it should be a cube here exactly, a square b the next term, a b square the next term, and b cube. Right. So how we have written this? So it actually follows a pattern. Right. So the pattern here is whatever the element which is present in the first place, the power of that element will be increasing starting from the index number. Sorry, it will be decreasing starting from the index number until 0. And for the second place element, it will be increasing starting from 0 until the index number. Right. So now I hope you guys have understood the second observation also. Right. So now we are going to deal our coefficients thing. So these are our main two observations. So now we have to, so amongst these identities, now we have got an idea like how many terms it will be there for any expansion, as well as what will be the exponents or the powers of the elements here. Right. So now the thing which should be required here is the coefficient. So we are now left with the coefficients. So if we could get a relation or the pattern for this, coefficient also, then it will be easy to write for any of the expansion. So we are actually remembering until a plus b whole power 4, for example. But if you could know if we could remember all these observations along with the relation of these coefficients, we can write for any of the power. That means we could able to write a plus b whole power 10 also, a plus b whole power 100 also, a plus b whole power 500. So for any of it, we could be easily writing. So now our aim is to focus and get the pattern for our coefficients now. So we'll be deriving that using the Pascal's triangle here. So let's write the identities. So a plus b whole power 0 is 1. So here the index is 0. So what is the coefficient here? 1. So let's write it here. And for the next one, a plus b whole power 1. That is a plus b. So what are the coefficients here? So 1 into a and 1 into a. So let's write it. So we are trying to form a triangular shape so that it is easy for us to remember. Right. So here 1 and 1 here. And for a plus b whole square, a square plus 2ab plus b square. That is nothing but here 1, 2 and 1. Right. So we can write that. So this one will be splitting like this. So if we know for index 0 it will be 1. So we can form like a triangle. So this will be splitting as 2. So for the next one again this will be 1 here splitting as 2. This also splitting as 2. That means here 1, here it will be 1 and from here also it will be 1. So 1 plus 1 it will be 2. Because we already know when index is 2 we will be having 3 terms. And when index is 3 we will be having 4 terms. So we should be splitting such a way that we could get 4 coefficients here. So again 1 will be splitted here. 1 will be splitted. So here 1. So here 1. So again 2 will be splitted. So 1 plus 2 here. Here 2. So 2 plus again from here 1. So 2 plus 1. This one. So this is 1. 2 plus 1 will be 3. 2 plus 1 will be 3 and 1. So it actually follows like a triangular pattern in order to get the coefficients here. Right. So let's write for 5. Right. So this one will be splitting like this. 4 twice. 6, 2, 4, twice, 1, 1. So here it is 1. Whereas here 4 plus 1 it is 5. And here 4 plus 6 that is 10 here. And here 6 plus 4 again 10 here. And here 4 plus 1 it is 5. And here 1. So how many terms we are having? How many coefficients? So 1, 2, 3, 4, 5 and 6. So when the index is 5 we will be having 6 terms in the expansion which will be having the coefficients to be 1, 5, 10, 10, 5, 1. Right. That means if I am having a plus b whole power 5, what will be my expansion here? So let's write. So for the first term, power will be decreasing. So it will be a power 5 into b power 0. For the second, it will be increasing. And the next, a power 4, b power 1. And the next, okay, let me do it this way. I'll just give a gap in order to substitute the coefficients that we have just got. So it will be a power 5, b power 0 plus a power 4, b power 1 plus this coefficient power will be, so first term power exponent will be decreasing. So a cube b square plus a square b cube plus a power 1 b power 4 plus a power 0 b power 5. So let's write these coefficients accordingly. So here it will be 1 into, so no need to write. Here it will be 5. Here it will be 10. And the next year it will be 10. And the next year it will be 5. And the next year it is 1. That means the expansion of this a plus b whole power 5 is given by a power 5 plus 5 a power 4b plus 10 a cube b square plus 10 a square b cube plus 5 a b power 4 plus b power 5. So this will be our expansion of a plus b 5. So likewise, we can write for a plus b whole power 6, a plus b whole power 7. But have you guys identified the thing here, while how we are actually getting the coefficients here? That is by splitting this triangle and adding it, and then we are actually getting it, which actually gets a lengthy, because in order to get some a plus b whole power 20, we have to start from the first step and then we have to go step by step, which means it's also it's actually consuming a lot of time here. There is no shortcut or trick here. So, but here this can be converted into another way. So let's see how can we do that. So we have seen the splitting here, the triangle splitting and addition of it. So just now we have seen that. So this triangle, Pascal triangle, can be rewritten using our C terms, that is NCR. Right, so just now we have seen it will be index 0, it will be 1. Index 1, it will be splitting, so it will be 1 and 1 here. For index 2, again, this will be splitting and this will be splitting. So here it is 1, here it is 2 and here it is 1. For index 3, again, I'll just keep the arrow so that no need to confuse here. So twice, it will be splitting like this, like this. So here it will be 1, 1 plus 2, it will be 3, 2 plus 1, it is 3 and here 1. Right, but these can also be written. So this one here can also be written as 0, C0. So 0, C0 is nothing but 0 factorial by 0 factorial into 0 minus 0, 0 factorial. So what is the value of 0 factorial? We have already discussed this while dealing our factorial property. So 0 factorial will be equal to 1. So this one can be written as 0, C0. Similarly, this one can be written as 1C0 because 1C0 is also 1 and 1C1. Right. So what we are trying to do is we are trying to establish some pattern, some relation in order to directly write any of the expansion. Right. So if we go this Pascal's triangle method and all, we have to start from the beginning. That means we have to start from the 0 index and then we have to split and we have to write for each of the everything. So that will actually consume a lot of time. If it is 100, we cannot able to write that. We couldn't able to do that. So that's why we are trying to convert, we are trying to rewrite this Pascal's triangle using our combination, using our C here. So let's try to focus and try to understand the observation, like just observe it how we are doing it. So 0, so this is our index, so it will be 0, 1 can be written as 0, C0. And 1 can also be written as 1C0 and 1C1. All these are nothing but 1. If it is for 2, we can write that from, so if we start from the index, so the power, the top one will always be the whatever the index, so it will be 2. See, here it will be starting from 0. So 2C0, 2C1 and 2C2. So 3 coefficients, enough. If we are having index 3, there will be 4. That means 3C0, 3C1, 3C2 and 3C3. Right. So comparatively, this will be easy, right? While without doing this splitting and all, addition and all. So how can we do that? It's easy that if I'm having a plus b whole power 5. So now I know what are the coefficients. So I'll just take my index. My coefficients will be starting from index. Here it will be 0. That means 5C0, 5C1, 5C2, 5C3, 5C4 and 5C5. Right. So just now we have seen using the Pascal's triangle, we got the values to be 1, 5, 10, 10, 5, 1. These are our coefficients. So using this rewritten method, that will be 5C0, 5C1, 5C2, 5C3, 5C4, 5C5. So let's check what are these values. So 5C0 here is nothing but equal to 1. Similarly, 5C1 equal to 5, 5C2 equal to 10. So there is nothing but the same thing. So now what can we do is, if we want to write the expansion of this a plus b whole power 5, the coefficient will be first coefficient will be phi c0, and this first term power will be a power 5 and second term power will be b power 0. And for the second, what is the second coefficient? Phi c1, and this power will be decreasing, so a power 4, and the second term power will be increasing, so it will be b power 1. Right, and for the third coefficient, so here it is phi c1, so next will be phi c2. So phi c2, this power will be decreasing, so a cube, and b power will be increasing, b square. And the next phi c3, and here power decreases, so a square, here increases, so a cube. And the next will be phi c4, and here a, here b power 4. And the last will be phi c5, a power 0, b power 5. So without any effort, without doing this splitting and all those things, we could able to write the entire expansion of this a plus b whole power 5 using the combinations and the observations which we determined previously, which we derived previously. Right, so likewise, the index value can be anything, even it can be 100, 250, 300, it can be any large number, we could be able to write it. Yes or no? But it will be going on like this, but we could able to write the expansion. Yes or no? So this is how we'll be writing any expansion. So this entire writing expansion is nothing but our binomial theorem here. So let's see our binomial theorem for any positive integer n, that is any positive index value. So far I have explained you with a number, with the index number. So now here we are trying to write a generalized form here. That is a plus b whole power n. So how the coefficient will start? The coefficient will start from nc, and here it will start from 0. So nc 0, and the power of a will be starting from the index, so it will be n, and here b power will be obviously 0. And for next one, nc, here it will be 1, and here this will be n minus 1, and here b power 1. Right, and for the next one, nc2, a power n minus 2, b 2. And the next one, nc3, a power n minus 3, b cube. So in another way, we could able to remember this expansion. So here you can see whatever number we are writing here, that will be subtracted from the power, so from the index in the power for the first term, and that number is directly given to the second term. So that's the another way to remember. So this is our generalized binomial theorem for any positive integer n. So I hope you guys got an idea and a quick understanding related to our binomial theorem. So let's do a question. Let's do a small expansion here. So here comes the question. So just expand it and let me know the terms here quickly. So first thing is, let me know number of terms. So first and foremost thing, let me know the number of terms and then do the expansion. So two things you have to do. So first thing, let me know the number of terms and then do the expansion of this given identity. Quickly guys. So I hope you guys got it. So if you have any doubts, any questions, you can feel free to ask me. I'll explain you again. So no issue in that. So come on guys, quickly do it. So let's see how many could able to solve it. So first thing is very easy. So what is the observation we have already derived? So number of terms will be 1 more than the index. So here the index is 4. So 4 plus 1 equal to 5. So So the total number of terms which we will be getting here is 5. So the term which is given here is x square plus 3 by x whole power 4. So you just have to expand it. So our general thing here is a plus b whole power n. So here in place of a, we are here in this term, in place of a, x square is given, and in place of b, 3 by x is given. So you have to do the expansion accordingly. So quickly guys, do it. So let's just erase this. So x square plus 3 by x whole power 4. So three things we have to remember. One is the coefficient, one is the first term exponent, and the other is the second term power exponent. So let's write the thing slowly. So first thing is our coefficient. So what is our index here? 4. So it will be 4c naught. And the other is our first term, that is x square whole power index, that is 4 here. And for other it will be 3 by x whole power 0. So this will be the first term. And the next it will be 4c1 and x square. So as I mentioned, index minus whatever the number here we are having, that is 4 minus 1. And for the second term, directly the number, that is 3 by x whole power 1. And third term, that is 4c2 x square 4 minus 2, and here 3 by x whole square. And the next term 4c3 x square whole power 4 minus 3, and then 3 by x whole cube. Next 4c4 x square 4 minus 4, and then 3 by x whole power 4. So let's simplify it. So 4c naught will be, I'll just write down here. So 4c naught equal to 4 factorial by 4 minus 0, that will be 4 factorial, and 0 factorial, which is equal to 1. So here it will be 1. So x power 8. So this will be 0. 3 by x will be obviously 0 here. Right. So just take your time and understand this, and then you can just do the simplification, I guess. So have a look, guys. And let me know if you have any queries in this expansion. So I hope no doubt. So let's do the simplification. So this is the first term and second term 4c1. So it will be 4 factorial by 1 factorial 4 minus 1, that is 3 factorial. Right, so this can be written as 4 into 3 factorial will be getting cancelled. So that will be 4. So 4 here. So x square 4 minus 1 3. So x power 3 into 2 6 and here 3 by x. And the next one 4c2, that means 4 factorial by 2 factorial into 2 factorial. So it will be 4 into 3 by into 2 factorial by 2 factorial into 2 factorial. So this will get cancelled and 1 2 will get cancelled. It is 6. So it will be 6. So 4 minus 2 2. So power will be 2 into 2 4. So x power 4. 3 square will be 9 by x square here. And our next term 4c3. So I'll just do it here. So 4 factorial by 3 factorial. 4 minus 3 will be 1 factorial. That means 4 only. So 4. So 4 minus 3 here 1. That means here x square. So 3 cube. That means 9 3s are 27 by x cube here. And the next one 4c4 will be obviously 1. And here this power will be 0. So this entirely x square power 0 will be 1. And here we'll be having 3 power 4, that is 27 into 3 will be 81 by x power 4. So let's simplify further. So x power 8 plus 4 into 3 12, x power 5 plus 6 into 9 54. So 54 x square will get cancelled. So it will be remained with x square only. So 27 into 4 8 28 108. So 108. So this x cube and will get cancelled. So in the denominator it will remain with x. And here it will be only 81 by x power 4. So this will be the entire expansion of this given term x square plus 3 by x whole power 4. Right. So this will be the expansion. Right. So I hope now you guys got an idea how to write this coefficient as well as the exponents of our first term as well as the second term. So now it will be easier when we do keep on practicing and keep on doing these things. It will become very, very easy for us in further. So let's do one more question and then we'll move into our next concept. So here I have given compute 98 power 5. So if you have calculator, you will just do the multiplication and do it. But instead, here you have to find manually 98 whole power 5. So can we do this 98 into 98 and then that into 98? So it will be a lengthy multiplication, right? We might miss some number, right? So that this 98 can be written as 100 minus 2. Yes or no? 100 minus 2 is nothing but 98. So in place of 98, we can write 100 minus 2. Then this will be turning out to be 100 minus 2 whole power 5. So which is in the format of a minus b whole power 5. Which means here we can apply our expansion. That means this will be 100 plus minus 2 whole power 5. Which means a value is equal to 100 and b value is equal to minus 2. So that's how we are going to do it. So let's now do the expansion of this. So because here we are having the b value which is a negative minus 2. So keep doing this and let me know the answer of 98 power 5, guys. I'm just looking for your answers in the comment section. So if you have done it, you can just give me the answer in the comment section. So let's see if anyone has already given me the answer, guys. Okay, I hope you guys are still doing it. No issues. So let's do the expansion according to our general method. So here what is our index? 5. So it will be, first coefficient will be 5c0. And here the first term, that is 100 power the index. So what is our index? That is 5. And the second term, that is minus 2. So whatever the number here, so 0. So it will be 0. So second term coefficient will be 5c1 and here 100 power n, that is index 5, minus this number, that is minus 1, and minus 2 whole power this number 1. So let's write the third term here. 5c2 100 power 5 minus 2 and minus 2 power 2. Fourth term 5c3 100 power 5 minus 3 and minus 2 whole power 3. So how many terms we have written so far? 1, 2, 3, 4. So how many more are there? 2 more. So it will be 5c4 100 power 5 minus 4 here and here minus 2 power 4. And the next, guys, so 5c5 here, the last term, 100 power 5 minus 5 and here minus 2 power 5. So this will be our entire expansion of this term, which is 100 plus minus 2 whole power 5. So now we have to simplify this in order to get our final value of our 98 whole power 5. So I hope you guys can do the calculation. So it's a bit lengthy, but I hope you guys got an idea of the concept of this expansion of our binomial terms. Right. So if you have any doubts, please let me know, guys. So let's do the simplification also. So 5c0 will be obviously 1. So 100 power 5. Right. So it will be 10. So here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And here this will be minus 2 whole power. So here it will become minus. So 100 power 4. That means this 5c1 will be 5. So 5 into 100 power 4. That means 1, 2, 3, 4, 5, 6, 7, 8. And then here minus 2 whole square will be positive. So here it will be plus. So 5c2 value will be 10, I guess. So 10 into 100 whole cube, 5 minus 2, right? So 1, 2, 3, 4, 5, 6. And then here minus 2 whole square will be 4. So this entire one term, so this second term, first term. And I'm just going to write the next terms here. So let me erase these terms and then we can write the remaining terms. I'll just erase it here. How many terms we have written already? So 3 terms we have written already. So I'm just eliminating those. So let's write the 4th, 5th and 6th terms here. So plus, sorry, 4th term, right? So it is minus 2 whole cube. That will become minus, right? So minus 2 whole cube will be minus. So it will be minus here. So 5c3 value will be around, let's see, 5C3 value. So 5 factorial by 3 factorial, 5 minus 3, it will be 2 factorial. So 5 into 4 by 2, that is 10 here. Right, so here 5 and here there will be 1, 2 and here 10 into this 2 and the next one will be minus 10 into cube. So 1, 2, 3, 4 into 8 and the next one will be 5. So 5 into 100 because it's only one time. So 100 power 1. So 100 into power 4 it will be 16 and the next one it will be 1 5C5 100 power 0. So this will become minus. So this is 1 and this is 0. So minus 2 whole power 5 will be minus 32. So these are the terms, so that you have to do the multiplication and all, which will be after simplifying it, the final answer will be 9039207968. So this will be the final value of this 98 whole power 5. Right. So I hope you guys, the whole idea regarding this solving this is to get an idea of how to expand our binomial thing here. Right, binomial term here. Right. So let's move on to our next concept. So the next concept we are going to discuss is deductions from binomial theorem. So we already know our binomial theorem, the general binomial theorem, which is given by a plus b whole power n is expanded as nc naught a power n b power 0 plus nc1 a power n minus 1 b power 1 nc2 a power n minus 2 b power 2. So and so on. Right, so this is our general binomial theorem. So using this expansion of general binomial theorem, we are going to deduct some expansions here. Right, so for the first one here is, in the expansion of a plus b whole power n, taking a equal to x and b equal to minus y, what will be obtaining? So here you have to substitute in place of ax, in place of b minus y. That means x minus y whole power n. So give it a try and write the expansion of this after the replacement of a and b values, where a has been replaced by x and b has been replaced by minus y. So quickly write the expansion for this and let me know, guys. So if you guys have any doubts, please let me know in the comment section. I'll be reading it and getting back to you. So the only thing we have to do is, so we have already known this general expansion. So in that, the replacement here is x, a equal to x and b equal to minus y. So let's see how you will be deducting this and what will be the final expansion after the substitution of this a and b values, x and minus y in place of a and b. So let's see how the result will be here. So the substitution term will be looking like this, x minus y whole power n. So this can be rewritten in the form of x plus minus y whole power n, just now how we have solved our previous question. Right, so then now it will be nc naught first coefficient x power n. So anyways this will become minus. And the next nc1 x power n minus 1 minus y power 1, so it will be minus y. And C2 x power n minus 2 minus y whole square plus NC3 x power n minus 3 minus y whole cube and so on, and the last term will be NCn x power 0 because x power n minus n here, that means it will become 0 minus y whole power n. So this will be the expansion after the substitution. So this can be simplified as NC0 x power n. Here it's minus y. So this can be, bring it on to the front side. So it will be minus NC1 x power n minus 1 by, and then plus minus plus minus. So here you can see that there is the alternative plus minus plus minus. So this expansion can be generalized and can be written as x minus y whole power n is equal to NC0 x power n minus NC1 x power n minus 1 y plus NC2 x power n minus 2 y square and so on. What will be the last? So we don't know whether it's plus or minus. So let's take minus 1 whole power n, because whether it's plus or minus depends upon the n index value, because that will be the power of our second term here. So it will be minus 1 whole power n NCn y power n, because at last term our x power will become 0, which is 1. Right, so this will be our generalized outcome or the expansion after replacing our a and b with x and minus y. So this is one of the deduction we can predict from the binomial theorem. So let's move on to the next deduction. So in this deduction, we are going to replace the a value is equal to 1 and b value is equal to x. So let's do this deduction and let me know the answer and the result here for this expansion. So just now we have seen one deduction. So I hope you guys might have got an idea how to deal with these deductions from binomial theorem. So I hope you guys can do this also. So quickly do this reduction and let me know the expansion, or if you have done it, you can just text me in the comment section. If you have any doubts, any questions while doing these reductions, please feel free to ask me and mention in the comment section so that I can get your doubt and I can solve it as soon as possible. So let's see, anyone has any doubts, any questions? So I hope no doubts yet. So I hope you guys are getting the concept. So solve this and let me know, guys. So once we done this second deduction, so we'll just wind up our session and we'll continue the rest in our next session. So let's see what is our general expansion. So it is a plus b whole power n equal to NC0 a power n b power 0 NC1 a power n minus 1 b power 1 NC2 a power n minus 2 b square and so on. The last term will be NCn a power n minus n b power n. Right, so the same way, the same expansion will be followed here, whereas the term will be turning out to be 1 plus x whole power n. So let's see this. So now the term has been turned out to be 1 plus x whole power n, because we have substituted in place of a, we have substituted with 1, and in place of b, we have substituted with x. So now the term has been turned out to be 1 plus x whole power n. So let's write the expansion. NC naught. So first term 1 power n, second term x power 0, and the next NC1 x, first term, right? So it will be 1. So 1 power n minus 1, and then x power 1, and the next NC2 1 power n minus 2, x power 2, and so on. Last will be NCN 1 power 0, x power n. So now if you observe here, the first term is 1. So whatever the power can be of 1, it will always be equal to 1. Yes or no? So now this term will become NC naught here. So 1 power n, it will be anything. The power could be 100,000, but still the value will be 1 only. So x power 0, 1. So it will be only NC naught. And here NC1. So this power anyway is 1. So we can neglect it. So it will be NC1 into x. And this is NC2. So this can also be 1. So 1 into something will be the same thing. So it will be NC2x square. And the next NC3 x cube. And so on. The last one will be NCN x power n. So now here you can identify that the expansion of this term 1 plus x power n has been turned out to be a very simplified version, which is equal to NC naught, NC1x, NC2x square, NC3x cube, and so on until NCN x power n. So this will be the easiest one of the expansion of our term 1 plus x whole power n. So likewise, by replacing in place of a and b, we could deduct many of the binomial deductions from the binomial theorem. So we have seen only 2 of the deductions from binomial theorem in our today's session. So the rest of the deductions and the remaining concepts that we are going to cover in our next session of binomial theorem. So I hope you guys have understood today's session very clearly. So I'll repeat that you guys just go through the session once again and let me know if you are facing any questions, any difficulties, any doubts in the comment section. In our next session, before starting the session itself, I can just clarify your question and we can start our next session. So that's all for today, guys. So I hope you guys got an idea about this binomial theorem and the deductions, how we deal with it. So the rest of the topics we'll just cover in our next session, and we are going to continue this deductions from binomial theorem in our next session. That's all for today. Thank you, guys.